Hello everyone, welcome back to Diksha Karnataka YouTube channel, and today in the Decode NCERT series we are going to discuss one of the smallest chapter of your class 12th or PU2, that is electromagnetic waves. So it will be not very long video, but I guess you will benefit from this if you watch this video from the beginning. And obviously you have to open your NCERT book along with me and follow through the book for your understanding, right? So here we are discussing most important concept from this chapter, EM waves. From there you might get some MCQs for your PU board, as well as some conceptual questions maybe come from for your KCET also. But this is not a comprehensive guide for KCET. For KCET we are already started another series. If you have not yet joined our channel, joined our WhatsApp channel, or followed our YouTube channel, do that so that you get the notification right away, so or you don't miss out on any of the videos that we are doing. So let's start with the introduction part. So in the introduction part there is a small thing that is mentioned, that the most important prediction emerged from Maxwell equation is the existence of electromagnetic waves. So Maxwell's equation or Maxwell's electromagnetic equation is very important if you study physics in future. This is one of the very important part. A complete branch of physics is based on this Maxwell's 4 equations, and you have to do them in detail. But right now Maxwell is the one who saw all 4 equations already existing, but he did one correction in one of the equations, and then he combined all the 4 equations already was there, and then he gave away his famous electromagnetic theory. Okay, and from that theory it is obtained that the speed of light is close to 3 into 10 to the power 8 meter per second, which is very close to the actually observed measurement. So basically this gives the theory a drastic improvement, saying that okay, your theory is correct. Right now, where did Maxwell did his correction? So Maxwell actually did the correction in a part called displacement current. What is the meaning of that? So if you remember, in Ampere's circuital law we said that B dot dl, closed integral of B dot dl is equals to mu naught into I, right? So that was the Maxwell's equation. Now that was the Ampere's equation. Now Maxwell argued that if we consider a surface like this, okay, and if we consider a surface like this, and a capacitor is getting charged, okay, and if you consider that the current is passing here, and if you consider a loop like this, so this is an Amperian loop. Now if you consider the Amperian loop like this, then it gives you mu naught I, right? Current in the circuit is I, so it gives you mu naught I. So B dot dl is equal to mu naught I, so no problem in that. But you can construct another same contour, but the region is different. So basically what he did, first he did a circle like this. Okay, he said this is the circle. Now circle, you can draw another circle having the same place, but it is like a 3-dimensional place, like, so you can consider this to be a cap. Okay, so first he did the cap was the circular cap. Cap means cap of a bottle. Let me explain it. So suppose you have a cap like this. Okay, so this is the opening side. So first he considered, okay, let's see, this is the Amperian loop, and through this the current is passing. So I will consider this loop, and I will calculate that current through this is I. So it will be B dot dl is equal to mu naught I. Now in the second case he considered the other side of the cap. So same circular area, same circle, but instead of considering this face, now he is saying I will consider the opposite face. And if while considering that, he realized that, so this is the behind shape. Now in this shape there is no current present inside this, right? So this is a capacitor. So in between capacitor, current charges are not flowing like a current, right? So there is a gap. So current suddenly coming to this plate, and then it is completely disappearing, then again emerging back from the other side. So there is no conductor between them, so no current is flowing. That was the logic. But then he said this is not possible, so there has to be something which is carrying the current through this gap. and that something he called is displacement current. Okay, what is displacement current? Displacement current is as long as the capacitor is charging, there is a change in the electric field inside the capacitor plate. So as long as there is a change in the electric field inside the capacitor plates, there is a change in the electric flux linked with the capacitor plate. So that is how he said the changing electric flux actually gives rise to a current, and that current is named displacement current. Okay, this is only between when there is no conductor, right? Now he said that the displacement current is basically given by this formula. Okay, this current he calculated it. He said epsilon naught d phi E by dt is equals to the displacement current, and then he modified the current formula. So in the Ampere's circuital law, mu naught I, so that I he corrected it to be IC into epsilon naught d phi E dt. So this is the conductor current that is being conducted by the conductor itself, and this is the displacement current component. So in the exam they might ask what is displacement current in an objective, in a 2-mark question. So you have to remember this is epsilon naught d phi E by dt. Okay, d phi E by dt is the rate of change of electric flux. Now be careful if they ask you the same question saying that what is Ampere circuital law, Maxwell Ampere circuital law. So this is the Maxwell Ampere circuital law, and here there is a mu naught. Okay, mu naught epsilon naught. Now this mu naught is coming because we know that integral b dot dl equals to mu naught I, right? So this mu naught is actually coming from the Ampere's equation. Okay, and be careful, this is displacement current. In the expression for displacement current, no mu naught is there. Okay, mu naught is not there in the expression for displacement current. So in the exam, definitely if it is coming as a objective question, they will ask you mu naught epsilon naught. So be careful, do not fall for the trap. Mu naught is coming from Ampere's law, not from the expression for displacement current. Now this is called Ampere's Maxwell law. This is the main correction of Maxwell. Now based on that he realigned the 4 equations already known. So this is the equation for Gauss's law, this is the equation for Gauss's law of magnetism. Okay, this is the Gauss's law for electric charges, electricity, right, static charges, but he mentioned it for electricity. Anyway, this is the formula for Faraday's law. So Faraday's law in terms of integration you can write it like this. Okay, and even though this explanation is not there in your syllabus how this E dot dl comes, Faraday's law says induced EMF, but induced EMF can be represented by E dot dl. Anyway, now this was Maxwell's correction. This one is the Maxwell's correction, and he then put together all 4 equations, and then he showed that it gives rise to electromagnetic waves. Okay, now when it will produce electromagnetic wave, very important. Neither stationary charges nor charge in uniform motion, that is steady current, can be sources of electromagnetic waves. The former produces, former means stationary charge, okay, former produces only electrostatic fields, while the later produces magnetic fields that however do not vary with time. So if the charge is moving with a constant speed, okay, this also does not produce electromagnetic wave. This can produce magnetic field, but that magnetic field is steady, that means the magnetic field is constant. Electric field will change. If the charge is moving, definitely electric field will change. So what is the condition for having an electromagnetic wave? You need a time varying electric field and magnetic field. That means electric field and magnetic field which can vary with time. That is very essential to obtain electromagnetic wave. Okay, it is an important result of Maxwell theory that accelerated charges radiate electromagnetic waves. So when you accelerate a charge, okay, its speed is increasing or speed is decreasing. Accelerate, it can increase, it can decrease. In both cases it radiates electromagnetic wave. Very interesting. Okay, so this is the very important part of Maxwell's electromagnetic radiation. So they might ask when we will observe electromagnetic radiation. Electromagnetic radiation will be observed only for accelerated charge. Now there is some history is given how Hertz Okay, I did some experiment and showed that actually how Maxwell's equations were correct. Then Jagadish Chandra Bose also did some experiment. So these are all mentioned in this portion. You can have a read at it, okay, if you are enthusiast about science history. Now, nature of electromagnetic wave, very interesting. So electromagnetic waves basically are waves where electric field and magnetic field are not only varying with time. Varying means it's like an AC, okay, but they are also perpendicular to each other. So electric field is in this direction, say x direction, then magnetic field is in the y direction. So electric field and magnetic field, they are mutually perpendicular to each other, and the direction of propagation of the wave, electromagnetic wave, is mutually perpendicular to all three of them. So it's like a left hand rule, okay, left hand Fleming's left hand rule. So this is electric field, this finger is electric field, this finger is magnetic field, then this will be the direction of propagation of wave, okay. And in terms of wave equation, because we are talking about electromagnetic waves, in terms of wave equation you can write Ex, that means electric field is varying only along x direction. Ex equals to sine kz minus omega t. What is the meaning of kz? Kz means the wave is propagating in the z direction. Similarly, By, that is the y component of magnetic field, other components are 0. So y component of magnetic field is B naught sine kz minus omega t. So it has to have two pairs, one pair, each of them has to be mutually perpendicular to each other, and they will propagate in the same direction. So this is the direction of propagation, whereas this represents the component along which the electromagnetic wave is varying. Sorry, electric field of the component is varying. And as the name suggests, electromagnetic wave, because electric field and magnetic field both are responsible for the generation of this. If you make magnetic field 0 or constant, it will not be an electromagnetic wave. Similarly, if you make electric field 0 or constant, it will also not produce any electromagnetic wave. Okay, here k is related to the wavelength of lambda of the wave and given by k is equal to 2 pi by lambda. Okay, interesting question, interesting part. Okay, so they might ask that write the equation for electromagnetic wave which is propagating along z direction. Then you have to be careful and you have to write it like this. If they ask you write an expression for electromagnetic wave propagating in the y direction, then electric field will be along x and magnetic field will be along z direction, whereas electromagnetic wave will be along the y direction. So you have to adjust it accordingly, but mostly if you remember this equation, that will sufficient for your PU board exam. Now speed is basically speed of light, and it is given by 1 by mu naught, 1 by square root of mu naught epsilon naught. Very, very important expression, again for objective you have to remember this. Another expression is B naught equals to E naught by C. This is also a very, very important formula for board exam, for competitive exam. And speed for any medium is basically 1 by square root of mu epsilon. Obviously mu naught epsilon naught is for free space. For any other medium it is 1 by square root of mu epsilon. Okay, now move on. Electromagnetic spectrum. Here we will discuss about different waves. So if you see, this is the spectrum diagram. It starts with gamma rays, generally having range from 10 to the power of minus 11 to as small as possible. So this is the wavelength. Now if you see that smaller the wavelength, higher is the frequency. So gamma rays, X-rays, ultraviolet rays, they are very high in frequency, whereas their wavelengths are very, very small. Small wavelength means it can penetrate difficult objects. For example, if you consider gamma rays, suppose there is a gamma ray source situated outside the studio room, then that gamma ray can still penetrate the walls of the studio room and can still reach me and still harm me. Okay, so gamma rays are something which has a very small wavelength. It can penetrate very thick lead, that is where it is kept, so radioactive elements radiate gamma rays. So they are stored inside a lead container. Lead means LED, lead container, okay, lead. Okay, so lead is basically the something which is used to store radioactive elements, because to prevent it from the gamma ray that is coming out of the in the nature, they should not come out. Okay, so that is one of the thing that you should be careful about. Okay, X-rays are also a thing that if you have ever broken a bone or you have done some surgery, then definitely you have done some X-rays of your hand, legs, or any part or other part of the body. Okay, you may have seen X-ray plates from your grandfather, maybe your father, or some other member of your family. So X-rays are basically used to take the picture of your bones. Ultraviolet ray, UV ray has a lot of application. We will see that in a while. One of the common application is water purifier. If you are drinking water, UV purifier. What is the meaning of UV purifier? Basically, they are using UV rays to kill germs present in the water. Now visible ray, so if you see the entire spectrum, visible ray is very small, and they have to zoom in to show you the entire range of the visible ray. Visible ray starts from 700 nanometer approximately 700, because the exact value is 670 nanometer for red. So it is starting from, a round figure is 700 nanometer to 400 nanometer. This is the round figure, not exact value, slightly less than 400 millimeter, slightly less, yes, slightly more than 400 nanometer, that is 420, 410, like that, and slightly less than that of 700 nanometer, that is 670 nanometer approximately. Okay, so this is the visible range, that is entire world that we see are situated only in this region. So imagine what would have happened if we could have seen gamma rays, X-rays, or other rays. Okay, there are devices, other devices which can actually see those things. Okay, some animals, for example, can see in ultraviolet radiation. Some animals can see in the infrared radiation, especially those who are nocturnal animals. They can see clearly in the infrared radiation. For example, owl is an animal who do the hunting in the night, so they can see in the infrared radiation. Dogs can see in the infrared radiation. Okay, some of the dogs. So this is the entire spectrum where we can see only very small portion with our naked eyes. Okay, now next is infrared. Infrared is when so for example, when earth is during the day, earth receives the heat energy from the sun. Now at night it radiates back that heat energy. That radiation is basically in infrared radiation. Our body, human body, always radiates heat in infrared radiation. Okay, so this is the basic function of infrared. Infrared can so that's why army can detect people who is moving in the shadows by using infrared radiation at night, because our bodies will emit infrared radiation. So if you wear a infrared radiation goggle, you can see whoever is moving in the dark. Maybe he is thinking, okay, this dark, I will not be able to he will not be able to spot me, but infrared goggle can spot, and even it can harm the people, right? You can see it, and you can shot down the terrorist who is trying to cross the border, maybe, right? So these are the very interesting application. Now microwaves, we have all seen microwaves. It is there in our homes. We used to heat the food inside the microwave. Okay, next is short radio waves. Short radio waves are also used in communication, form of communication. Television and FM radio, we all have heard songs from our favorite channel in FM radio. Okay, and television obviously is there in our homes. Then we have AM radios. AM radio was older generation radios when there was no FM radios possible, so only one broadcast used to come from the central radio station that is located in New Delhi. Okay, Prasar Bharati. So it was called Vividh Bharati. So different languages at different times it used to telecast news, then sports. Okay, so there is a tournament going on between India and England, right? So in those times, any tournament between India and England was very big news. Okay, and there was no televisions. So during 60s and 70s, AM radio used to broadcast those live telecast of the matches through radios. Okay, so AM radio was that. Nowadays it has reduced its application, very often not often used. Next we have long radio waves. Long radio waves are used for purpose of radar. Okay, you can detect it, any distant object. Long distant communication, as the name suggests, long radio waves, it is used for long distant communication. Okay, so for communication, radio waves are used. Microwaves we already know. Now let's see some other details. So radio waves are used for cellular phones. Use radio waves to transmit voice communication in the ultra high frequency band. So ultra high frequency band, cellular communication happens. So that means short radio waves, basically short radio waves are used for telecommunication, whereas television and FM radio already is there in the middle band, then AM radio, then long radio waves. Long radio waves is for long range communication. Okay, next is microwaves. Let's see some of the application of microwaves. The frequency of the microwaves is selected to match the resonant frequency of the water molecules, so that the energy from the wave is transferred efficiently to the kinetic energy of the molecules. This rises the temperature of the food containing water. So what basically it does, if you have seen a microwave basically, if you put the food inside the microwave, close the door, rotate the knobs, it will heat the food as if something is happening inside. But if you open it, the inside of the microwave still remains cool, but how it is able to heat up the food, that is some invisible thing is happening, right? So that is what that gives rise to a confusion that microwaves is harmful for human. Actually it is not. What is happening is that there is a slightly higher wavelength slightly smaller wavelength compared to radio waves are actually microwaves. They are like radios. Microwaves are part of the larger microwave family. Anyway, so if you see the water molecules, they have a specific bond length, okay, and the microwaves wavelength are actually same to that of the bond length of the water molecules. So what is happening when these microwaves are passing through water, they are actually vibrating each and every molecule of the water, okay, because microwaves are vibrating and their wavelength is equal to that of the bond length of the water. So they are actually communicating with the water and making them vibrate along with the microwave. Okay, so that's microwave is transmitting the energy directly to the water molecules, and then these water molecules also gain that energy. And gaining energy means what? Gaining energy means it will eventually convert into heat energy, and that heat energy slowly transmit to the other food particles, and it heats up. Okay, if you are heating something in a microwave which does not contain any water, you cannot heat it up. So for example, if you put some dry rice inside the microwave, it will never ever it will heat up, okay, because dry rice or dry wheat, they do not have any water, sufficient water content inside it. Okay, if it has enough water inside it, then only it can cook it. Okay, not cooking, basically it is mainly used for heating purposes. Okay, so microwaves basically can only work if the element has some water in it. Without water it cannot work. Okay. Now, infrared waves are produced by hot bodies and molecules. For I have already given you examples. Okay, infrared detectors are used in Earth satellites, both for military purposes and observe growth of crops. So from top, okay, from the space, infrared radiations are happening. Okay, infrared radiation, they are monitoring how much crops are going. Based on that, the prices are set. Okay, if you heard that due to rain a lot of crops are wasted. Now how it is done? Yes, when there is a rain, you can go to the ground, you can see how many hectares of foods are wasted, or what you can do, you can from the space you can see, okay, this area is water logged. That means from that area you will not receive any heat. So if you not receive any heat, that means that area is completely gone, that food grains that present in that area is no longer available. So this is how the government or the planning commission, they determine, okay, maybe this year we will have a shortage of food, so we have to supply the food from our storage. So the government has some storage kept for this particular purposes. Every year they refresh the stocks, they sell some of the stocks, they replenish the stocks, but sometimes if there is a rain or any other calamities, they use that stock to keep the prices under control. Okay, so both military purposes and observe the growth of crops. Electronic devices, for example semiconductor light emitting diodes, also emit infrared and are widely used in the remote switches. So if you see remote control, let me show you. So this is a remote control device. Okay, this is a remote control device, and here there is a infrared light. Okay, you cannot see this using your naked eye, but if I just maybe press some light, if you are able to see it or not, let me know. But if you don't able to see it using your naked eye, so what you can do, you can take your mobile phone and open the mobile phone camera, switch on the video mode, and then you press the remote control of your whatever remote that you have in your home. Okay, and then you record it. After recording, you will be surprised to see that you cannot see that in your naked eye, but the mobile camera can see that. So it will give you a bright spot in the mobile camera. So that is a very beautiful thing. So basically that signifies that that is a light emitting diode which is sending signal to the TV through which you can communicating with it. Okay, so which channel you want to watch? You want to watch some sports channel, education channel, or news channel, or watch some cartoons. So whatever you are doing, that signal is being sent by that tiny diode. Now the sun is an important source of ultraviolet light, but fortunately most of it is absorbed in the ozone layer in the atmosphere at an altitude of 40 to 50 km. UV light is large quantities, has harmful effects on humans. So basically sun emits a large amount of UV rays, but those UV rays do not reach us. They mostly get absorbed in the ozone layer. If there is no ozone layer, like say for example moon or say Mars, okay, they cannot have you cannot have a life over there without using spacesuit. So if you go into the International Space Station, you have to wear the space suit when you are traveling there, or inside the space station they have some protective things, but as soon as you are coming out of the space station, again you have to wear those protective astro suits. Why they are important? Because they are something which will protect you from the external cosmic ray and UV rays. UV rays is very dangerous, and if you are exposed to UV rays for a longer period of time, your skin will darken and slowly your body may develop cancers. Okay, so that is why long exposure, long and overexposure to UV rays is not good. So nowadays we say we apply some sunscreen lotion, says UV sun protection factor. So that is basically protective from UV rays. Not all the creams that you use are protecting you, but there are some which can protect you. Okay, during our time we used to remember there was a fast bowler, Alan Donald. He used to lot of that cream on his nose. Okay, so that was a fashion back then. Now, due to its shorter wavelengths, UV radiations can be focused into very narrow beams of light for high precision applications such as LASIK. LASIK is where your eye power, if you have a power in your eye, that can be operated using LASIK to correct your refractive power in your eye. Okay, assisted in the situ keratomyolysis eye surgery. Next is UV lamps are used to kill germs in water purifiers. UV lights are also used to sanitize surgical equipment. So before surgery, all the equipment has to pass through UV rays, so that if there is any germs, any things are present inside that surgical equipment, they are all killed. So this is called sanitization using UV rays. Now ozone layer we already know that our ozone layer is in danger. So if you do not stop using CFCs, then we used to have a lot of CFCs in the past till 90s and early 2000s, but nowadays there was a Geneva Convention where they have signed a treaty that no one will use CFCs. So previously all the ACs, fridges, refrigerators, they use CFCs. That was a coolant gas. Now we do not use use CFCs, we use different gases. Okay, CFC is chlorofluorocarbon. It's an organic gas, but still it is very harmful. Next is X-rays. X-rays are used as diagnostic tool in medicine and as a treatment for certain forms of cancer. So X-ray is one of the rays which can cure cancer, or it is basically focused into the cancerous cells to kill those cells, and it can be used, okay, as a part of chemotherapy. Similarly, gamma rays are also used in chemotherapy. So radioactive elements, as I mentioned, they emit gamma rays that can be used to kill cancerous cells, but it can kill healthy cells as well. They do not discriminate between cancerous cells and healthy cells. So when someone goes through chemotherapy, that means their cancerous cells are died, but also their healthy cells are died. That's why chemotherapy is not always considered to be a good case of treatment. Now, different types of electromagnetic waves. So there is a table of all the waves and their detection, their production, etc. I would have liked if they have given application as well, because that is the question that you see in your exam, right? Now you can read the summary, okay, and you can see that E naught by B naught is equal to C. So in the chapter they have given some different formula. Here they have given some different formula. Okay, so E naught B naught is equal to E naught by C. That was the formula that you have to remember. C is this. So these are all the important formulas given in the summary. With this, I will like to conclude this chapter, and maybe next time I'll be back with some other chapters if it is left. Till then, bye.